Video, we're going to start Unit 2. So I have the Unit 2 Part 1 Skeleton Notes. This unit is all about alcohols. We're going to learn about chemical reactions generally, and then acid-base chemistry, acid-base reactions. So this aligns with the ebook Chapter 3. I have the learning objectives here. So we will expand what we know about IUPAC nomenclature to include alcohols, amines, and nitriles. And I have these numbers in parentheses here because alcohol nomenclature isn't talked about until Chapter 8, Section 2. Amines is Chapter 23, Section 1. Nitriles, I couldn't actually find in the book, but I still want to teach it to you all so you know what nitriles are. So if you did want to look back at the book, that is where to look for alcohols and amines. We will use the curved arrow notation to show electron movement that represents bonds breaking and forming in chemical reactions. The next three learning objectives are focused on acid-base chemistry, so we'll predict relative acidity or basicity of a molecule based on a few different factors. We will really dive into this proton transfer mechanism step, which is a acid-base reaction step. And then we will use pKa to solve different equilibrium problems and predicting the structure of a species present in solution at a certain pH. So that gives you an overview of the whole unit. We're starting with adding some notes to what we already know about nomenclature. So this is part 2 of nomenclature notes. Our IUPAC rules, we're going to expand them to include priority groups. So when a molecule includes a priority group substituent, these are certain substituents. We're going to learn 3 of them for this unit. But when you have priority groups, the highest priority group receives the lowest number possible. So we take that into account when numbering carbons in a chain. And it's included as a suffix in the molecule name rather than a prefix. So far, all of the substituents we've learned about, we include in the name as a prefix with its number. When there is a priority group, the highest priority group is included as a suffix, so at the end of the name. So we're going to learn about 3 priority groups in this unit. That is the nitrile group, the alcohol group, and the amine group. So a nitrile group is a carbon that's triple bonded to a nitrogen. An alcohol group is an OH that's bonded to the rest of the chain. And an amine group is a nitrogen, and that nitrogen could be bonded to 2 hydrogens or 2 R groups, and I'll talk about what R groups are soon. Looking at these notes over here, so I do want to say there are many more priority groups. We will learn a few more this term and definitely more in organic chemistry too, but for now we will only be naming molecules. If they have a priority group, it will be one of these 3. Note 2. So the nitrile group starts with this carbon right there. That carbon is numbered as part of the parent chain. Usually when we're talking about substituents, they come off of that parent chain. With a nitrile group, that carbon will be carbon 1 when we number the molecule. I have an example of that coming up. So then if a nitrile is in a molecule, if a triple bond to a nitrogen is in a molecule, the suffix will be nitrile. So at the end of the name, we will use nitrile to indicate there is a triple bond to nitrogen. When we learn more priority groups that have higher priority, and if nitrile is in a molecule with a different higher priority group, then we can't have 2 suffixes. It will just be a prefix cyano. Now we won't use this unit because these 3 groups here are listed in increasing priority. So nitriles of these 3 have highest priority. And then amines will have lower. So if you have multiple priority groups in a molecule, you have to identify which is the highest priority based on this ordering. And again, I have an example of that coming up. Okay, then alcohols, that is when there's an oxygen bonded to hydrogen. We will see many, many, many alcohol molecules. If that's the highest priority group, then it gets this OL ending, same as the end of the word alcohol. And then if a different higher priority group is present, it is listed as a prefix, ordered alphabetically, and you'd use hydroxy. Then an amine is when we have a nitrogen bonded to the parent chain. That nitrogen can be bonded to 2 hydrogens or 2 R groups. So here's note 3. R groups, that R is used widely in chemistry. You will see it a lot. And it just is used to represent the rest of a molecule, a hydrocarbon chain. So if you see NR2, the R could be methyls, so it could be N bonded to 2 CH3 groups, or it could be ethyls, or it could be a methyl and an ethyl. There's just 2 different hydrocarbon chains. R is used when that chain isn't important. It can't be used when you're naming a molecule. You would have to specify what those R groups are. But for example, in this table, it doesn't matter what that R group is. If there is 2 hydrocarbon chains bonded to that nitrogen, it's still an amine group. Now in our class, we're only going to learn how to name NH2 substituents. And that is named using amine if it is the highest priority group, or amino as a prefix if it is not the highest priority group. Okay, let's look at some examples. I think that will help solidify the content that we're looking at here. So here are 3 molecules, and I've got the structure and the name. Let's look at one at a time. This first molecule, now I know the name is there, but let's still think about the carbon chain substituents, where they are. So we have a 4-carbon chain. We need the substituent to have the lowest number carbon, so we'll start on the right side, just like we would for any substituent. So this is a butane chain with an alcohol on carbon 2. So we put that together. There are 2 ways to do it. I suggest this first way, but you may see the second way. You can submit the second way. So I just want to show both. So because the alcohol is the priority group, there's only one priority group and it's the alcohol, we use the suffix OL. So we write the carbon chain, the number where the alcohol is, and then OL ending. We still use dashes between letters and numbers. 2-butanol, the second one that's listed here, is okay because the 2, there's only one thing in the name that could receive a number, and that is the alcohol. So it's okay to put it in front. But like I said, I recommend the second one because if you do have more substituents, then you need the 2 to be right next to the OL. Again, you're going to see both, so just want to make sure you can interpret both. Okay, next we have another molecule. Again, before we look at the name, let's just dissect the carbon chain and what's here. We have 2 priority groups, an amine and an alcohol. To give these lower numbers, we still have to number at the end of start numbering at the end of a chain. So we'll give this carbon 1, 2, and 3. Now we have another substituent as well, methyl group here. So how about I highlight the parent chain like we've done in class? This is our parent chain, those 3 carbons. We have an alcohol on carbon 1, an amine on carbon 2, and a methyl on carbon 2. So let's just list these elements of the name out like we normally would. So our main chain is propane. On carbon 1, we have an alcohol, and on carbon 2, we have an amine. So the higher of the 2, the higher priority of these 2 groups is the alcohol group. So the 1 gets OL, the 2 gets amino. And then 2 also has a methyl. So now higher priority group gets the suffix, so that 1 all there is at the end of the name. The parent chain is right before it. And then all other substituents, so the amino and the methyl, are listed first alphabetically. So we put amino before methyl. Here we have the last one is an example of a nitrile containing compound. Now don't forget about note 2, oops. Note 2, where the carbon that's part of the nitrile group is part of the parent chain. It's counted as a parent chain, part of the parent chain. So this has to be carbon 1. Let me use my pink for numbers. 1, 2, 3, and 4. So we have a 4 carbon chain. We have a methyl on carbon 3. And it is a nitrile. It's on carbon 1, but it has to be on carbon 1. We have to give that carbon the lowest number because it's the highest priority group. It has to be at the end of a chain because that nitrogen can't bond to anything else. That carbon can't bond to anything other than carbon 2 and the nitrogen. So I don't think you'll see the number 1 in a nitrile name. Sure, it's possible, but it is not needed. So again, let's put the name together. Parent chain right here. Oops. Butane, butane. Nitrile group, that gets the suffix because it's the highest priority group. And then the last substituent is the methyl on carbon 3, and that is included as a prefix. Okay, so those are some examples. I wanted to break those down to show how this nomenclature is applied. I have 3 learning checks here. How about we do the first one and then I'll save the second 2 for class so we have some practice to do when we come back as a group. Okay, so this first molecule, we have a ring. I see that there are 6 carbons, so I'm going to go ahead and write cyclohexane. I see a methyl group and I see 2 alcohols. So the only priority group here is the alcohol. But there are 2 of them. So just like other substituents, if there's 2 of the same thing, we use di. So this will be diol. And then we have methyl. Now all we need is the numbers. We need to give priority groups lowest number possible. And we have lots of locations where we potentially could start numbering in a ring, but we want lowest numbers overall and especially low numbers for the priority groups. So this will be 1, 2, and 3. So we have 1, 2, diol, and 3 methyl. So putting this name together, we have only prefix is the methyl. So 3 methyl. The diol will be the very end of the name, so we go right to cyclohexane. And then we have 1, 2, diol. I left off this E. I'll be honest, I won't be picky about that E. It's left off if the next letter is a vowel, like butanol. We don't have that E after butane because the next letter is a vowel. But here, technically, the next letter is that di, is the D, which is not a vowel, so it should be included. That's not what I want students to get tripped up with at this point. I want you all to be able to put these names together. As those questions arise, send them to me and I'll give you direction in that way. Okay, I will not go through the next two. We'll do those in class. You could try them before class as usual. Instead, we'll move on to the next page, chemical reactions. So this is where the beauty is in chemistry, at least that's what I think. This is where you can start with something and make it something completely different with different properties. This is how medicines are made. This is how different materials are made. Food can be made synthetically. Flavors and fragrances. I think it's super cool. So a chemical reaction, just in its most basic definition, this is a process through which one or more substances, I'm going to skip the parentheses for now, one or more substances are converted to one or more different substances through bond breaking and or forming. So the things that get converted, what we start with, those are called either reactants or reagents or starting material. I'm going to use all three of those terms, so you will definitely see them throughout the semester. And then what gets formed is a product. So we use this arrow in between reactants and products. And to go from reactants to products, we have bonds breaking or forming. To remember what bonds are, a covalent bond is sharing of electrons. So when bonds are breaking or forming, this is electron movement. It all has to do with the electron. Now we can use what we know about molecules, like their polarity, bond length, bond strength, and so on, to predict how reactants will react and then form products. So we're going to learn how to do that for a number of different reactions this semester. The acid-base reaction is just the first one and the simplest one. And then we'll learn a few more. Now, still thinking generally about reactions, curved arrows are used to keep track of electrons. So I said this all has to do with electron movement. Well, curved arrows show that electron movement. We've used this for resonance. So this is really similar to resonance. They look the same, but instead of showing electrons resonating within one molecule, they will show electrons moving between molecules to break or form sigma bonds. So an arrow can show bonds breaking, it can show bonds forming, and then each arrow has an arrowhead and a tail. So the tail is the start of the arrow. So this is where the arrow originates. It must be at a lone pair or a bond. It has to start at electrons. It cannot start at an atom without electrons. It has to be at a bond or a lone pair. And then this is where electrons originate. So this would be an area with electron density. Usually our arrows will start at an area of high electron density and end at an area of low electron density. So we're going to add a little note here, an area of high electron density. Then the arrowhead, this will be the end of the arrow. This could be at an atom or a bond. It shows where the electrons are going through that reaction, and usually is an area of low electron density. Electrons being negatively charged are attracted to areas that have less electrons, so that would be an area of high electron density. Electrons may move to an area of low electron density. So the most important thing to remember about curved arrows is that they show the movement of electrons. When you see an arrow, I want you to think about electrons, where they started and where they're going. Where they started is the tail of the arrow, where they're going is the head of the arrow.